talked about solving exact equations, but what if an equation isn't exact? Is there any way to make it exact so that we can take advantage of the same methodology to solve it? Well, yes and no. So the methodology that we're going to use, the approach that we're going to use to solve these guys or make them exact is basically very similar to what we did with linear differential equations. Namely, we're going to introduce an integrating factor and multiply the whole thing by, the whole equation by, and make it exact. But sometimes the expressions that are going to lead us to the integrating factor are just going to be too messy and complicated, so we don't want to even deal with it. It's not worth it. Let's go ahead and dive in and see how this works. So if you remember, if we have an equation of this form, and it's an exact equation, then my has got to equal nx. The partial with respect to y of m has got to equal the partial with respect to x of n. In other words, this expression should be 0, my minus nx. But if this equation isn't exact, then this expression is going to be non-zero. And what we do when it's not exact is we take this difference and we first divide it by n, and we hope, and we do a little bit of manipulation in algebra, and we hope that we can end up with a function that's just in terms of x. If we can do that, then we're golden. We can just construct our integrating factor very easily, integrate it and put it inside an exponential, and that's it. We multiply the whole equation by it, and there we go, we got an exact equation. That doesn't work. In other words, we don't get a function just in terms of x. Then we have a second option. We're going to do the same thing. We're going to take, this time, nx minus my, and we're going to divide it by m. And if that gives us a function just in terms of y this time, then we're still good. That we can construct our integrating factor just as easily. But if neither of these two work, in other words, we don't get a function of just x here, we don't get a function of just y here, then the function, we really can't make it exact with any elementary methods. So let's go ahead and really the biggest part to worry about is the manipulation that's involved in making this function just a function of x, right? Because usually it's not going to just, all the y's aren't just going to cancel themselves, all the x's aren't going to cancel themselves here. You're going to have to do a little bit of manipulation in algebra. And it's kind of hard to see exactly what to do, because you're just going to be looking at an expression and saying, what do I factor? How do I get rid of these y's? And so that's the part that you should sort of try to buckle up and try to pay attention to. So let's go ahead and do an example and see how this works. So we have this equation that kind of looks exactly like an expression plus an expression times y prime. So let's go ahead and test it to see whether it is. So if this were m and this is n, if I calculate my and nx, I should get the same thing, right? So my is going to be 3x plus 2y, and nx is going to be 2x plus y. Okay, so these two obviously aren't the same thing. I can take the difference now. I'm going to start the process of making this guy exact. So I'm going to take my minus nx, and I'm going to divide it by n, right? So my minus nx, 3x minus 2x, x, 2y minus y, y, so x plus y, and then n is x squared plus xy. Now, this doesn't look really that good at first glance, but like I said, you have to be very patient with these expressions. You're not going to see it immediately. It's not as easy as, just factor this guy out and it's done. This one is pretty simple though. All you have to do is just factor out an x in the denominator. You're going to end up with an x plus y over here and an x plus y over there, so they cancel, and you're going to end up with 1 over x, which is just a function of x, which is exactly what we wanted. But like I said, be a little patient with this process. Don't just immediately preclude the possibility of there existing some method of getting rid of the y's, okay? So mess with it a little. Let's go ahead and construct our integrating factor. It's just going to be e to the integral of 1 over x dx. That's just e to the ln x, and that's just x, right? E and the ln cancel each other out. So our integrating factor is just x. I multiply the whole equation by x. So I'm going to get 3x squared y plus xy squared, and then plus x to the third plus x squared y prime is equal to 0. So now what I'm going to do is check to see whether this is exact or not. I'm supposed to have an exact equation. So if I took this guy's partial with respect to y and this guy's partial with respect to x, should get the same thing. So let's go ahead and try. This guy's partial with respect to y is going to be 3x squared plus y squared. I'm sorry, 2xy, x. And then over here, this guy's partial with respect to x is going to be 3x squared plus 2xy. And indeed, we have the same thing. So this equation is, in fact, exact now, and you can solve it very easily using the method that we learned in the previous video. So as you can see, it's not hard. It's actually a very easy process making an equation exact if it's constructed in a way so that you can make it exact. Otherwise, it's very hard. But like I said, the only tricky part is this and knowing when to give up and say, okay, no, there's no way I can do this. Usually, spend half a minute at least on it. Make sure you've exhausted all the different methodologies on, just manipulation techniques and everything that you can think of. But other than that, there you have it.